All right, everyone, welcome back. We're going to continue with our third part of our measure theory review. Today we're going to talk about sizes of sets. In particular, today we're going to define a measure. Now, just to remind everyone where we're going with this, especially if you haven't seen measure theory before, what we're really asking is, what we're trying to do here is define the notion of like the size of a set. Okay, so, if you see, something that looks like this, okay, this is a set, or it's a little domain or whatever, and we'll call it A. Okay, well, we want to ask the question, how do I measure the size of that? Okay, well, you might think, okay, well, this is some integral or whatever, but it's not, always that simple. Your set is not always going to look that nice, especially if you're working, let's say you're working with data, right, and it's a little discrete or whatever, so the point is there's many different notions of defining the size of a set. What we're trying to do is make it really general. So, like, if you come along with your own creative notion of what size should be, you can. This is to give you the tools to now build your theory based off of that. Okay. So, for example, when we integrate, we are assuming something about our notion of size. So let's say I have like a function here. This is f, and I want the area under the curve. Well, you probably remember from calculus, right? Let's say I want the area from A. That's not an A. That's an A. I want the area from A to B. Okay, well, you do this like game where you cut it up into little strips or whatever. You play this little game where you cut it up into strips and then you make smaller strips or whatever. And then to find the area of the strip, you can take a left endpoint, right endpoint, center endpoint. You just take some value f, let's say it's c, and then you multiply it by the length of this interval. So we'll just call that L. Okay, so that area is equal to f of c times L. Okay, now that L is what we're really going to talk. I mean, this is really what this section is for. What is that L going to be? And because we can make integration better than this method, which you learn in calculus, this Riemann integration method, and it allows us to integrate more functions. Okay, so if you're looking at this at a 30,000 foot view perspective for why we're talking about measures, what we're trying to do is generalize this notion of length so that if you're solving a problem and you want to change the notion of length, perhaps you want this L to be something different. Okay, it could be L could be the probability that your, I don't know, electron's sitting here. I don't know. Okay. But if you want to change it, you don't have to reinvent the wheel. Okay. What we're going to do today is give you the outline of, okay, if you redefine this notion of L, how do you define an integral? How do you define this and that? Okay. So that's why we're defining a measure. Now, we just defined sigma algebras. And you may ask, well, why are we defining sigma algebras? Because we need to talk about what you can measure, because there's limits to that based off the properties you want, okay? Because we are going to want our notion of size to satisfy a couple nice conditions so it's easy to work with. And these conditions are intuitive, right? Okay, so like if I split this set in half, for example, and I want to measure the size of this set, I should just be able to measure this and then add it to this. Right? I measure these separately and then add them together. Okay, we want our measure to satisfy that condition. But to do so, okay, it turns out just putting that restriction, intuitive restriction, we want to be able to split things up and separate and add separately. That means we actually restrict ourselves to what we can measure, believe it or not. Now, we're not going to come down to those little nitty-gritty examples, but we will. That's kind of the reason we're talking about this, okay? So how do we as mathematicians and physicists or even engineers define a measure? Well, it's quite simple. So we defined what a sigma algebra is. We know what a set is. Okay. So given a set, so to define a measure, we need two things. We need a set and we need a sigma algebra over that set. All a measure is, right? Okay, a ruler, you put it up against something and you get the length, okay, anything like that. You fill up a cup, that's you're kind of measuring volume, whatever. You're just getting a number. So a sigma measure, or you can just call it a measure, like if we know the sigma algebra, All it is a function from that sigma algebra. Okay, well, what does that mean? Let's stop for a moment. That means my input is a set. So I'm plugging in a set to mu. This is the Greek letter mu. And I'm getting out a real number from 0, it could be 0, including 0, to infinity. Okay, now you've noticed I put the closed bracket here. That means our measure can be infinite. I can have something that's infinitely large. And that makes sense, right? When you're working in math, you could have a line that shoots off to infinity, and you can say, oh, well, that has infinite measure, okay? So we're trying to keep things intuitive. So that's it, but we ask 2 additional conditions. The first is more or less a technical one. It's saying there exists some A in my sigma algebra that has a finite measure. Right? When we say finite measure, we mean mu evaluated at A is less than infinity. Okay? This is a technical condition because if everything in your set has infinite measure, well then, it's not a very interesting measure. Okay, so we just require this first condition. And it's countably additive. So I talked about this idea earlier. We should be able to split sets up or measure things one part at a time. So if I have A and I have B here, and I want to talk about, the measure of A union B, that's both of these sets. Well, because they're disjoint, they're not touching each other, right? I should be able to say, right, intuitively, we want our measure to satisfy this relation. Okay, so now this extends, in our definition, we take it a little bit further, not just finite collections of sets, but countably infinite collections of sets. Not uncountable, just countable. So meaning if I have a sequence of, so countably additive, this is what we require our measure to be. If we're given a sequence of pairwise disjoint sets, what does that mean? Well, that means here, let's draw this or whatever. If I have given any 2 sets, AI and AJ, if I intersect them, it should be empty set when I is not equal to j. So any 2 sets don't touch in my collection. If I'm given a countable sequence of such sets, where if I pull 2 out of the sequence, they don't touch, they're disjoint, then measuring over their union means measuring them all at once is the same as measuring them bit by bit. Okay, and that's a measure. That's it. Very simple definition. Now, we have some additional definitions, some terminology to keep in mind. The first is defining a measure space. So I'm going to kind of switch over to different language now, since we're kind of getting into measure theory. So a measure theory is a collection, X sigma mu, where X is a set, sigma is a sigma algebra over X, and mu is a sigma measure. Okay, very simple. So we call that a measure space. Now there's some special types of measures we should talk about. If it happens to be that mu, our measure, does not take anything to infinity, we call it a finite measure. That's pretty intuitive. The second condition, which is a little bit more involved, is that of mu being a sigma finite measure. What that means is we can represent our entire space X as the union of countably many sets with finite measure. So a measure mu is called sigma finite if there exists a sequence in sigma with each element of that sequence having finite measure. And we can write X as the union of this sequence. And in a moment we'll cover an example of both of these. Right? So let's continue and talk about some examples of measures. And this is perhaps maybe the simplest. This is called the counting measure. And this is quite important because in statistics or anytime you're working with discrete data, this is a great measure to work with. Okay, so we're going to let X denote the natural numbers, so 1, 2, 3, etc. And we're going to let sigma be the power set of the naturals. Okay, again, this is a sigma algebra as we've proved before. The power set of any set is a sigma algebra over that set. And we're going to define mu to be the counting measure, which takes every set in the power set, which is the same as saying every subset of the natural numbers, 2, either the number of elements of A if A is finite. Okay, so like if I have A is equal to 1, 2, 3. Let's see. Okay, well, it has 3 elements. So if this is A, then mu of A is equal to 3. Okay. Now, if A is infinite, okay, like for example, if I say, the set of evens, which is infinite, there's infinitely many evens, we're going to say that measure, we'll say that's B, we're going to say that mu of B is equal to infinity. Okay, so this is not a finite measure. That's the first thing you can notice. Because we have sets in our power set that map to infinity, particularly the set of evens, this is not a finite measure. Now, we've been throwing this term measure around. Let's go ahead and walk through a proof that this is actually a measure. Okay, so we need to verify 2 conditions. We need to first verify that there is an element of the power set which has finite measure. We have that right there, but we'll write it down again. And then secondly, we need to verify that given a disjoint sequence of elements in the power set of the naturals, that mu is countably additive. That means taking the measure of the whole thing at once is equal to just summing up the measures of each part. Okay? Proof is not too bad. We'll just start it here. So first, we need to verify that there exists some A in the power set. This symbol means there exists, such that mu of A is less than infinity. Well, this is obvious. So just take, set containing 1, just an element of T. Or you could just take the empty set, or whatever, it has no elements, so it would be 0, the measure. Well, but in this case, mu of the set containing 1 is equal to 1. Okay, that's no big deal. Now the second, we're going to need to play some case chasing. Okay, so we're going to start, right? We need to verify that if we have this pairwise disjoint sequence, okay, keep in mind just a note, subset, right? This is a set because it's a sequence. There's multiple sets in it, and this is a set. Okay, so when I say subset, every set in this sequence is a set of the power set. That's what, again, just to explain things so you get used to this notation. This is really for people who have not seen measure theory before. Okay, so we need to also verify that if we have a sequence in the power set of the naturals that is pairwise disjoint. Okay, meaning that AI intersect AJ. They have no common elements for I not equal to J. Then, okay, so how we're going to prove this, we're going to assume we have this sequence, and then we want to prove, so then we need to prove that mu, the measure of the union of AN, is equal to the sum from n equals 1 to infinity of mu AN. Okay, so that's what we need to prove. Okay, so let's maybe do a different color here. So we're going to say let AN be a disjoint sequence, or pairwise. I'll just write PW for pairwise in the power set of the naturals. Okay. Now, think back to our definition of mu. It depends on what the set is. Okay, so if my set is finite, I just count the number of elements. Okay, now, but if my set is infinite, then the measure of that set is infinity. Okay, but now we're dealing with, so here's the question, now we're dealing with countably infinitely many sets, right? So each set could be something different. So we need to consider different cases. Now, if we look at this here, we can see that if one of these sets are infinite, because we're combining them all together, if just one of these sets is infinite, then this whole thing is an infinite set, this union. So therefore, this measure should be infinity. And the same thing on the right-hand side, right? Because if one of these sets, right, if like an or ak is infinity, we know that this side will be infinity, okay? And we know that in this sum somewhere, we'll be measuring that infinite set. And then that will be infinity. And we adopt the convention here, and I should say this, convention, that a plus infinity is equal to infinity for any a between 0 and infinity, including infinity. So we take infinity plus infinity to be infinity. 5 plus infinity is infinity. 4 plus infinity is infinity, etc. Okay. So anyway, but the point is we have these cases. So we'll consider, we have two main cases. Or I'll just write it here. We have one case, which is one of these sets in the sequence are infinite. One of the A1, A2 are infinite. Okay, that's one case. Okay, I'll write that here. And then the second case, maybe I'll use a different color, is all of the AN, A1, A2, etc. are finite. Now with this we have two subcases. So I'll call one case 2A and the other one 2B. There's two subcases. So if all of them are finite, okay, either infinitely many are non-empty, or only finitely many are non-empty. Okay, so why did I break it down this way? Well, this we discussed why that's intuitive. Okay, well, if none of them are infinite, then that means all of them are finite. But we still have two cases. Why? Because if you look to this sum here, even if all of the AN are finite, this sum can still be infinite. Because if I have infinitely many positive terms over here, right, then what will happen is that I have an infinite sum. This becomes infinity. Okay. Now, and the same is over here, right? If I have infinitely many, and remember these are pairwise disjoint. Okay, so when I say if infinitely many are non-empty, I'm adding infinitely many terms to this union. Okay, to this set right here. So this would be infinity. That's one case. And then the other case is only finitely many are non-empty. Okay, and in that case, only finitely many of these measures have a positive value. So this is a sum of a finite amount of positive numbers. So this would be finite. And then likewise over here, if only finitely many are non-empty, then this becomes a finite set. You see there's different cases. And I'm just going to walk through them so we can be thorough. Okay. So this one, I think we're clear on why this is the case, right? If one is infinite, well, I guess we will just walk through it. Okay. So if, let's say, AK, which is an element of the sequence AN, is infinite, then what do we know? Well, we know that if we union anything with K, we get an infinite set. So we know that the union from n equals 1 to infinity of AN is infinite. And then we also know that because this is infinite, we know that the measure of AK is equal to infinity. Okay. So because this union is infinite, we know that its measure, by how we define the counting measure, is going to be infinite. So I'll write union AN. I won't write the indices. We know that that's infinity. Okay. Now, moving on to the measure of AK. Because this is infinity, right, when I talk about the sum from n equals 1 to infinity of mu AN, right, that's, measure of A1 plus the measure of A2 blah, blah, blah. And then eventually we hit the measure of AK, and we continue. Well, we know that the measure of AK, this is infinity. And it doesn't matter, remember, the measure is positive. A measure only maps to 0 to infinity. So all of these are positive numbers, and some might be infinity themselves. So this will be infinite. This whole sum right here will be infinite, okay? And we're done because we've proven that the measure of all of them together is equal to the measure, the sum of the measures separately. And this concludes case 1. Okay. Maybe I'll move this. Now we'll deal with the second case. I'll move it down here. Okay. So now we have the second case. So we're going to start with the fact that, all of these are infinite, or excuse me, finite. So let an be a pairwise disjoint sequence of finite sets in the power set of n. Okay, and so we just consider 2a and 2b. So in the case 2a, we'll say suppose infinitely many of the ANs are non-empty. Okay, so they each contain some number, at least one, right? It could be 1, 2, whatever, or 0. Excuse me, no, not 0. 0 is not in the naturals, at least by my definition. Okay. Besides that, so suppose infinitely many of the ANs are non-empty. Okay. Well, if that's the case, then this right here, this union, is infinite. Why? Because I'm unioning, even though these are finite, right? Let's say, for example, A1 is equal to the set containing 1. A2 is equal to the set containing 2. And I union all this. Well, I get the natural numbers, okay? Even though, and that's an infinite set, even though each AN is finite, okay? So since infinitely many ANs are non-empty, and none of them share elements in common, this union here is infinite, okay? So we get that the measure here is infinity. Now with the sum, it's kind of like the same story. Okay, so if I take the sum, n equals 1 to infinity of mu an, we know, okay, infinitely many of these sets contain one element. Okay, so that means infinitely many of these terms are at least 1. Right? Because that's how the counting measure is defined. It's just the number of elements in each set. So if there are infinitely many terms of the sum that are greater than or equal to 1, infinitely many, and I'm adding them all up, I get infinity. Okay? And these two are equal. And that takes care of case 2a. Okay, so now we're almost done, which is finitely many are non-empty. Let me move this down here. So let's save ourselves a little bit of trouble. So let AN be a disjoint sequence of finite sets in Pn, and only finitely many are non-empty. Okay, so we're just going to play the same story again. We're going to look at the union first, and then we're going to look at the sum. When we look at the union, okay, because only finitely many are non-empty, okay, well, the rest are empty. So this is really just a finite union. You can call it like A and 1, union A and 2, blah, 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 union A and K. These are the elements of this sequence which are non-empty. Right? Because if I put empty set here, it doesn't matter. Okay. And these are all finite sets. Okay. So, and these are also disjoint. So I'm going to call, when I take the measure of this, I just add up the elements in each of these sets. Very simple. Okay. And that's going to be like if this, has, let's say, number of elements. I don't know how I'm going to say eta n1. This has eta n2, blah, blah, blah. And then eta nk, right? Because these are all disjoint. It's kind of clear. Well, the measure of this union is literally, eta n1 plus eta n2 all the way to eta nk. And you can probably see how I'm going to finish this. It's the exact same thing when I look at the sum. So when I look at, from n equals 1 to infinity an, right? Because only finitely many are non-empty, and we know that the measure with the counting measure, and it will actually turn out with any general measure, the measure of the empty set is 0, right? This is just, simply the measure of a n1 plus the measure of a n2 all the way to the measure of a nk. Well, that's just this right here. Okay, so it's countably additive, right? We get the same result. And we've covered all of our bases, right? We've covered case 1, we've covered case 2a, and we've covered case 2b. And these are all the cases, as we've discussed. And we conclude, that mu, which is the counting measure, is a measure on the power set of the naturals. Okay, so we have just proven that this is a measure. Now we'll move on to, this is a really easy measure, and it's quite an important one. So again, both of these measures are kind of important just to keep in mind. Let's say you've already taken measure theory, you're watching these for review. If you're going to write anything down, I would just write the definition of the counting measure and the one we're going to discuss next. Okay, this is called the Dirac measure. And for the sake of time, I won't prove it's a measure. It's very easy to do so. But we're going to say we're going to let x be any set, and we're going to take sigma to be the power set of x. And then what we're going to do is we're going to pick any point we want of x, but we need to mark it as special. So I'm going to say fix a special point. We'll call it, x naught in x. And then we define the following. Well, this is called the Dirac measure. I'm going to use the letter mu, but you'll also see it as the Greek letter delta. Okay? The measure of any set A is equal to, it's either two cases, just like last time. 1, if x naught is in A, in 0, if x naught is not in A. Very simple. I saw in the first video, someone here is in computer science or something. This is like, I don't know, true or false. That's what this measure does. It tests whether the statement x naught is in A is true or false, given any set A I have, any subset of my set X. Okay, and what can we say? We're not going to prove it's a measure. It's very easy to do. If you are confused about this definition of measure, this might be an enlightening example to do. But just looking at it, okay, mu never takes an infinite value. Mu never takes an infinite value. So we can say that mu is a finite measure. Okay, that's one thing we can say about it. With that, we can call this also not the Dirac measure, but also the unit point mass measure at x naught. Okay. So these are some two examples of measures. And before we go, I just remembered with this counting measure. Okay, we talked about a finite measure. This is a sigma finite measure, right? So this is a sigma finite measure. Now that's kind of easy to see, right? We were talking about earlier, I can write, the natural numbers as this union. I'll just say the union from n is equal to 1 to infinity of the set containing the n, right? That's going to be 1, union 2, union 3, blah, blah, blah. Once I combine all that together, I get the natural numbers. And with respect to my counting measure, each of these have finite measure. So I have written the natural numbers as the countable union of sets with finite counting measure. Okay, so this is a sigma finite measure space. Okay, so there's your example. We got a finite measure, we got a sigma finite measure. Next time when we come back, we're going to talk about some properties of measures that are going to be useful just to have under your belt. And then once we've gotten through that, we'll define the Lebesgue measure and get going on some integration.